Now starting. All attendees are in listen-only mode.
Welcome, everyone, and thank you for joining us today. My name is Kara, and I'm with the LTAP Center here at ODOT, and I'll be your host for this webinar. Today's webinar is Verification of ODOT Rock Channel Design Procedures, and we're thrilled to have Danny Shea as the presenter. Before we begin, I'd like to cover a few housekeeping items to ensure a smooth webinar experience for everyone. If you have any questions during the presentation, please use the questions panel on your screen. You can type your questions there and we'll address them during the Q&A session at the end. If you're experiencing any technical difficulties or have any other issues, feel free to use the chat panel to communicate with our team and we'll do our best to assist you. Please note that this webinar is being recorded and the recording will be made available to all registered attendees after the session. All right, with that out of the way, let's get started. It's my pleasure to hand it over to Danny Shea. Danny, the virtual floor is yours.
Thank you, Kara. You can hear me okay, right? Yep, okay. My name is Danny Shea from Ohio University. I was just presenting a project that we just finished. It's called Verification of ODOT Rock Channel Design Procedures. Started about 2 years ago, and we'll share what we have found. So first of all, I want to introduce our team. Besides me, we have Dr. Sam Curry, grad student, Moon Kareem, Jay McCarthy. We also have our partner, Dr. Jeremy Bricker from Zamkin from University of Michigan, A. Robinson, Dr. Kevin White, and Naramond and Zari from University of Akron. So I'll start about the problem statements and then the research background and then our approach and then what we have found and some limitation of this project and what will be some recommendation that we discovered. So rock channel protection is basically Riprap, which places the outlet of culverts, and it is to dissipate energy. And RCP, so-called rock channel protection, called RCP, provides stability against erosion of stream and bank. So the way ODOT designed RCP is this chart, figure 1. It is from the L&D manual, figure 1002-4. So the way to use this, it's for your culvert size, right? So these are, you see, you have 12-inch, 24-inch, and all the way to 120-inch, and you have a velocity at the outlet, right? So let's say, let's look at one example. Let's say for 12-inch culvert, and the velocity at the outlet is 12 feet per second. Then you will go to this point right, then you look at the RCP length, and also this is 4. Right? 4 means we have an 18-inch or 6-inch rock, so type C or dumb rock type. So this is how currently these RCP is designed. So the interesting thing is actually no one knows where this figure came from, and it's been used for decades, but no one actually knows where it came from. So it was thought to be from biology in '66, but actually that's not the case. So actually, still no one knows. No one is where this who designed this chart. Anyway, but have been used for decades. So that's several, and so the objective of this study is to see can we improve or verify the current. What we decided to do is to have 3 different velocities in our experiments. It's V1, V2, and V3. So V1, it's when it's the velocity that initiates scour, V2 is when the scour depth is developed, and V3 is when the velocity is so high, it's actually moving the rocks or the collapse of the reps. So this is the three velocity we'll try to do in our experiment, which I'll show in later in this presentations. So other than our universities, Michigan's partner will also do the experiments. So just confirm. We'll try to just ensure the data is just ensure the results are verifiable, and just also keep tracking each other's work. And I'll present the result in the later slides. And okay, so I want to talk about the research approach. So we'll do scale modeling. So meaning, obviously we cannot do a full size actual model. So we'll do scale modeling, and to do scale modeling, we'll make sure that the scale down version, they are geometrically, kinematically, and dynamically similar, which I'm going to show you how we're going to do it. So first of all, we have to design the scaling factor, this lambda. So literally, it's the subscript P mean prototype, M means model. So in this case, will be a dp will be the diameter of the culvert, and we take the prototype divide by the model pipe size. That will be our lambda. And also because this is a open channel scenario, so we take the flow number, set the phone number of the prototype equal to the phone number of model. So then the velocity would be this scale lambda to the raised to the 1/2. So that's how this how we compare the scale to prototype velocities. So the design parameters, the outlet velocity at the culvert end, the culvert diameter, and then also the length, the type, and the thickness of the RCP layers, and also the type and composition of the stream bed materials. So on both sides, our OU side and Michigan side, we're gonna do 15 experiments. So these red dots are the experiment we're gonna do. So basically, we're gonna choose a 12-inch, 48, 72, 96, and 120-inch culvert, but these will be scaled down. Okay, and we're gonna run each of these dots. We'll try to achieve the initiation of scour. V2 is the velocity where the scour hole is fully developed. V3 is when the rocks start to move, right? So we'll create 3 sets of curves and compare to the current ODOT chart and see where ODOT this current sets of curves it's see where they're at. So we'll show you the results later. So 3 different scaling factors, 12, 24, 30. So these are primarily due to probably the physical limitation of our flumes. So some of the higher culverts are 120 inch, suppose 10 feet large. We'll use a larger scaling factors, which will show you the design table in a minute. Okay, so rock solid collapse. Okay, so both side, outside and the Michigan side will create 3 sets of graph, and we'll show you the result later. So those 3 types of actual rock used by ODOT is type A, type B, type C. Those will also be the scale down, and so these type A, B, C. It's from ODOT CNM specification 703-19B. Okay, so I think most of you in the audience probably familiar with these type of rocks. So we literally just scaling down by sieve analysis. So let's say, for example, for type A rocks, so tell you what, it's a 2.5. Oh, so 2.5 inch sieve and 2 inch sieve and 1/2. So we literally did a sieve analysis to create type A, B, and C rock. So this is when we use lambda 12. So these will be the composition of the scale RCP materials. For 24 and 30 lambdas, we also see them in the same idea, but with different sizes of sieves. Okay. So we have some sample pictures that we did. So if this is lambda 12, so these will be the type A rock, and type B rock, and type C rock. Obviously, with different scale factor will be different size, right? So on the outside, we literally need to build a flume, and but this frame is actually from a previous ODOT project. So we use the materials, and then we built wooden flume, and we put sand to mimic stream bank materials. So this is our setup. We have two big tanks, a pipe, and we have a flow meter here. And so this looking the culvert materials, and with the pipes outlet here, and we have cameras meter here to measure the flow rates. Okay, so this is a 3D drawing drawn by two big water tank, and fits into a pipe, and the flow meter will measure the flow rates, and this is our flip like that. Okay, that's another angle. So those 15 experiments, those red dots that that I showed you earlier, so these will be the setup. So some of the experiments using the factor of 12, the scale factor lambda 12, some with 24, some with 30. It's mainly because of the physical limit of our flumes. So I say, for example, for a 48-inch prototype culvert, using a factor of 12, so that means the scale diameter will be 4 inch, and the length of LCP based on the design chart I showed earlier would be a 9.5 inch, and the thickness of LCP will be 1.5 inch, and so you can see you just basically just divide your prototype size by lambda to get the scale size. So 15 of those. All right, so this is more and it's the length. Here's thickness. I think it's thickness, and so those are the 15 experiments, and each of those experiments will get V1, V2, V3. Okay, so this is one of the experiments. So the way we did it is to this experiment, for example, this is case number 14, which that case is using 24 of scaling factor, which means the scale culvert diameter is 4 inch. This 4 inch, and LCP length is 15.75 inch, and the thickness is 2 inch. Okay, so these right here, so these are top-down pictures. So this is the initial condition, and once we observe the motion of sand or triggered scour formation, this will be our V1. Okay, so we look at what's the flow rate there, and then go back here. So then we'll keep going to get V2, which the scour hole depth is formed. So here the way we look at it is because we put a geofabric underneath the sandbed. So we just see black spot, which means all the sand is already eroded. So that means that which is equal to the thickness of the LCP itself. So then once we observe that, we look at the velocity. In some cases, V2 and V3 they are the same, meaning into the scour hole. So this is how we do all the experiments. It's another example. So anyway, so we'll just keep looking at using the top camera initial conditions. They get V1, V2, and V3. V3 here you can see that's a rock falling, right? Falling into the camera to capture what is the water level in the culvert, and what is the velocity. We also did some scan using a software called LCP is doing to protect the bed material being eroded. So anyway, so we also have each of the experiments and all those surface. So this is Michigan side. Michigan, they have a large teaching flume, open channel flume. So it's quite long, 60 meters long. The concept for is similar. They also set up a bed area, culverts, and end plates. So the different lambda, different scale factor, and yeah, so it's very similar. I think we're almost the same except for one or two experiments. So again, also same thing. You get those velocity V1, V2, V3. So similar approach. The concept is similar from both sides. So this is the top camera. So they have different, and then once you see the geofabric underneath, so that means the scour has been developed, and also the movement of rocks. Right? So those V1, V2, V3 for each of those experiments. Okay, so this is the LiDAR scan from the flume. And both sides we also import into MATLAB in this case, so we can do some further studies if needed. So I want to show you some of the results here. So this is from our flume. So V1 is when the scour hole start to form, right? So there's no clear pattern. So this is the let's say this blue curve is 12-inch. There's really no clear correlation. That's sort of all over the place, which probably true because how you determine the initial of the bed materials, it's somewhat subjective. So I didn't really expect we'll see any meaningful relationship for V1. V3, we'll talk about V2 later. I want to show you V1, V3 first. V3, in some cases, are equal to V2, and also it's many cases not necessarily the rocks start to move by water. It's actually the scour is large enough, so then the rocks start to fall into the scour hole, and also there's no clear pattern. They're like intersecting each other. So that's V3. Okay, V2, however, V2 actually is a much nicer relationship. And so it's an example. Let's say for a 12-inch experiment. So you can see the clear relationship with increasing value of the LCP length, and each of those curves that distinguished, right? And what we did, this graph on the right, is to regress them, get a regression to fit all this line here. So it's a 12-inch, 48-inch, 72, 96, and 120-inch. And to compare the how these curve to the current ODOT design curve. So this top line right here, this top curve is the current 120-inch LCP length curve. So it appears to us our curve shift to the right of the current ODOT design chart. So this is a little messy, but we just overlay our curve on top of the current conservative, which means they let's say for a particular point, I'm going to say let's say for 120-inch right culvert, the current ODOT method is more conservative, and for most of the cases, except for 12-inch culvert. So for Michigan, V1 is also a little weird. There's really no clear relationship, which is the same because and again how to determine V1 is somewhat subjective, right? V3 on that side, it's also very similar to what we observed. It's a sometimes V3 is very similar to V2, and so compared to the current, and this is V2. This is V2 from Michigan. So this is the current 120-inch LCP length curve, and this is what as to compare to Michigan obtained from the experiments. So they tend to be shifted left of the current design graph. So using V2, there is Michigan flume, but the dashed ones are the curve obtained from OE flume, and the solids are the curve from Michigan flume. So the LCP length based on Michigan data tend to be generally longer than ours, and so after seeing this, right? So then we try to figure out, hey, what exactly did we do differently? Because conceptually we are doing something. So why our curve and their curve are different? So there's some operational differences that we discover in Michigan. The teaching flume is a recycling system, right? And in our flume we are using two giant water tank to drive the flow. So we mainly use head to drive the flow. And in Michigan, the constant flow rate is the same for 5 minutes to observe the changes in sand bed. In our case, we just gradually increase our valve to get those velocity for each experiment. So these are the operational differences. The flume in Michigan, they narrower than ours. So the Michigan flume is about 2 feet in width, and ours almost probably 3.75 feet. That could make some difference in our results. And we also look at the flow regime from both sides. Our side, I think we're almost all supercritical flow, meaning the flow number is more than 1. We calculate the outlet flow number. In Michigan, they're mostly subcritical or near critical. So one of the things that we found out is that because the Michigan flume, they're recycling the water, right? And we just let the water, and then we didn't care about where the water goes. So our water is not recycled, and because of that, our flume, the sand bed in our flume, was fully saturated, and because Michigan flume, they'll have to use filter to filter out the water, right? So the sand will not get into the system. So they can see the sand bed materials. So Michigan, they're partially or partially saturated and or remain unsaturated, the sand bed materials. So under saturated conditions, the scour conditions occur at lower velocity than unsaturated conditions, and also explain why the curve is shifted to the left as compared to ours. Under saturated condition, the pore space between soil particles are filled with water, reducing the effective stress within the soil mass. And so it makes the soil more susceptible to erosion and failure. Okay, and also the flow condition. The outflow regime in Michigan Flume is mostly critical, subcritical, excuse me, or close to critical. In our case, it's almost, I think it's all supercritical, right? All supercritical. So using our curve that we develop, we also interpolate the remaining type size. So say the on the left is from OU. So we have those solid dark line. Those are actually what we did, right? And then we interpolate them to get 24, 36, and then remaining size, type size. And for Michigan also, right? So they have the five curves, and we also interpolate them to get a 24, 36, 60, 84, and 108 culvert size. So limitations, we decided to go with medium sand. The reason is because if we use anything small, finer than medium sands, we might not be able to see what's happening. The water will become coffee, right? So and also if soil that getting if we use like anything like clay or anything, it will be more cohesive, which is not what we want. We want to create a somewhat the worst case scenario. And the slope of the culvert or the actual stream bed might take an effect, but all our experiments with their level is zero slope. And also the we only tested circular culvert, but other like the box culvert or arch culvert we didn't do them. It's outside of the scope of this project. And also a tile water depth, right? That can also affect the flow regime at the outlet. So that's some of the recommendations. So for the graph that we developed from both schools, so for supercritical regime, maybe designer can consider using the OU graph. For subcritical regime, maybe the Michigan graph will be more suitable. And for soil saturation condition, right? So if the soil is going to be saturated, then the OU-based design graph may be more suitable. For partially saturated conditions, then the Michigan graph may be suitable. So for future recommendation, if future researcher want to take look at it more, maybe you can test each of these in-outlet outlet control culvert to see how the RCP will work against under these scenarios. Consider inlet outlet control based culverts and also post installation inspection as a proactive measure. And rather than, as one of the things that we discussed internally, it's maybe use flow rate instead of velocity. That could be a consideration for critical factor. So that's the end of this presentation. I want to thank ODOT. I want to thank the project manager Jennifer Spriggs and the tech. There's a lot of people here, but anyway, these are all the hydraulic folks in the ODOT. Anyway, so that's the end of this presentation. I'll take questions, Kara.
Wonderful, Danny. Thank you so much. Let's see here. Does anyone have any questions that they would like for Danny to answer for them? Please feel free.
Sorry, my speaker. my speaker was off. Can you say that again?
Oh, yep. I was just asking if there was anyone that had any questions that they could send them in, because right now, so far, Danny, we don't have any questions. So it sounds like maybe you hit all of the good information.
It's a lot of information, but I'll be giving the same talk at ODOT. So if any of the audience want to talk to me and discuss this, you can find me at ODOT as well.
Oh, wonderful. Yes, I'm so glad you said that. We do have a question though. We have a person that would like for you to explain the difference between the linear scaling and the F number scaling in determining the size of rock to test.
Jeremy, you want to answer that one, Jeremy?
Yes, sure. Can you hear me okay?
Yep.
Okay. I think the question means what scaled linear, also scale linear. Geometric scaling is 16:1. The velocity scaling is going to be the square root of that, or 4:1, meaning that if we have a 4 foot per second velocity at prototype scale, that'll correspond to a 1 foot per second velocity at model scale. And so, and that's standard in laboratory hydraulic experiments to use Froude scaling, because that's the scaling that produces equivalent thresholds of motion for any object, meaning it's where the lift force will overcome the gravity force, or where the drag force will overcome the friction force. If we want those forces to scale correctly, we have to use the Froude scale, and that's where the velocity becomes scaled by a square root instead of by a linear scale like the geometric scale is. Hope that answers the question.
Thank you so much for answering that question. Okay, if there's a follow-up question, please send that on over. Next question is, why do you think that the partially saturated conditions under higher velocities ended up being less conservative than the ODOT charts despite the higher effective stress?
Yeah, that's a good question. So since we don't know what the ODOT chart is based on, it's hard for us to really to answer any why questions based upon it. I mean, in general, what we do know is that, as Danny said, the saturated conditions experience a lower effective stress, so the sand is easier to scour. Unsaturated conditions where the sand is wet but not buoyant means the sand is the heaviest. They'll experience. One thing like is an important difference between the Ohio and the Michigan experiments is that the culvert outlet could be supercritical versus subcritical. But regardless of whether the outlet at the culvert is supercritical or subcritical, once the flow so implies to us is that once the flow is out of the culvert outlet and it's affecting the stone and the sand bed, the stone carpet and the sand bed, it's already subcritical. That means that regardless of whether the velocity of the outlet is supercritical or subcritical, it's going to have a similar, for a given flow rate, it should have a similar effect on the RCP and the sand downstream in either case. So what that's telling us is that it's not so much a function of the speed it's coming out of the culvert. It's a function of the volume flow rate coming out of the culvert. Because what for a given volume flow rate, like a given amount of liters per second or cubic feet per second, once it's out of the culvert and over the RCP, it's going to behave the same regardless of whether it came out of that outlet subcritical or supercritical. So by parameterizing the required RCP length as a function of culvert outlet speed, without taking into account whether that outlet speed is subcritical or supercritical, appears to be missing something. Whereas if we parameterized it as flow rate, that would give a more universally applicable answer. And if that's not clear, happy to discuss that more.
Thank you so much. Okay. Do you only recommend figure 1002-4 for relatively low slope outlet, culverts not outletting to a bend, and then above that going to something like HEC 23DG4?
Danny, I'll give you that, Danny. I don't know which number means which offhand. I'm sorry.
Again,
Can I say something real quick, Danny? Sorry, this is Kevin.
Go for it.
In general, the procedure used in the HEC publication is fairly conservative in the sense that it only looks at a native material and determines what's the scour hole of that native material and then just fills it with stone. And that's how they come up with those lengths. So generally speaking, the HEC method is somewhat conservative. And so in terms of the rock that you use, the other thing I would mention is when we're talking about rock, everybody realizes that, or everyone should realize that it's not meant to be a unlimited longevity installation. Even if you read through the HEC says that in every major storm you should go out and check the rock. The rock is meant to be somewhat sacrificial. So I think we want to do our best, but it's not. It isn't intended to be a lasting forever solution. It's meant to be a sacrificial solution. So I think I wouldn't get hung up on if it's a level bed or a non-level bed or anything like that. I'd more be looking at it from the sense of here's our general trends, and this is what we can draw from the general trends. So does that make sense to everybody, I hope?
They said that makes sense. Thank you so much.
Mm-hmm.
And and we said that we have someone that says that they appreciate all of the answers, and that they are doing research also, and they spend a lot of time worrying about correctly sizing the RCP. So they appreciate you very much.
Cool. Thank you.
All right. Does anyone else have any other questions before we wrap up? Okay. Well, it doesn't look like we have any more questions. So on behalf of LTAP and ODOT, I'd like to thank Danny Shea once again for sharing their valuable knowledge and expertise with us. As mentioned earlier, the recording of this webinar will be shared with all registered attendees, along with the PDF of the presentation. And thank you all for attending, and we hope you found this webinar informative and engaging. Have a wonderful rest of your day.
Thank you, Kara.
Thank you.